Hello student to the Foundation of Classical Electrodynamics course. So, under module 3, today we have lecture 52 where we discuss the Amperes law. So, we have lecture number 52 today. So far whatever we have done, let me quickly write down. So, the divergence of B we found 0, that is for magnetic field always the divergence is 0, showing that the magnetic monopole does not exist. Also, if I do the curl of magnetic B, it should be mu 0 J, that is the Amperes law. And we will going to derive this today. But before that, let me recap quickly what we have done. We done the Biot-Savart law. And in Biot-Savart law, it says that if I have a wire having some length, say dl prime, and the current is carrying, the amount of current that is passing through this wire is I. So, it should produce some kind of magnetic field at some distance, say at this point the magnetic field that should be a function of r, and if I have the length here say r, so this quantity is mu 0 divided by 4 pi mu 0 I, and then integral dl prime cross unit vector r divided by r square, and this r is measured from some coordinate system is here. So, from that I can measure this r, the location of this point with this from this coordinate system. Okay, so in terms of the current density J also one can find out this expression, and if I do, the expression should look like this way. It is mu 0 divided by 4 pi. This is the direct consequence of the Helmholtz theorem that we discussed in the last class, J r prime, and then cross r minus r prime whole divided by r minus r prime cube and dv prime. This is a volume integral. When we apply this Biot-Savart law to some standard problems, say in the first problem, that is if I have infinite wire and if I want to find out the magnetic field where this wire is carrying a current I, and if I want to find out what is the magnetic field at this point, then we take a small section dl prime, this is the length L, and then try to understand this distance where say r and do some calculation, but eventually we get this value. So, my B at say this is distance S. So, B at S, that was mu 0 I divided by 2 pi S and then phi. This is for infinitely long wire. Then another case we discuss where we have a current carrying ring, and this is the axis of symmetry, and over the axis of symmetry we try to find this was dl prime and the current was I, and if I want to find out the magnetic field here, then the magnetic field, so if this is r vector and if this is A, then the magnetic field should produce some distance like along some distance like a direction like this, but there will be they will form like cone, and this is my dB prime and r will be along this direction. This is unit vector r. So, we calculate it and we find that the value magnetic field is mu 0 I, and then if this is z, then mu 0 I a square divided by 2 of a square plus z square 3 by 2, and that was in z direction because the horizontal component will cancel out and we have only one direction along z. This is the z unit vector. So, that was another problem, and if z is equal to 0, then we had b equal to mu 0 I divided by 2 of a z unit vector, that is the center of the ring. So, that was the current carrying ring, and if I want to find out the magnetic field here at the center, then that was the value dl prime, and we calculate, and this is a. So, at z equal to 0, this is the point where the magnetic field will be this amount. And then we calculated the force. So, that was case 3, and 2 wire was there like this carrying current I1 and I2, that was say wire 1 and wire 2. The force between these two we also calculated, and the value that we got is say F1, the force is mu 0 I1 I2. If the length is L, then it is L, it is 2 pi d r 1 2, that was the value. And F2 was mod of F1, the amplitude is same, only the unit vector was from this side to this side, that we all calculated. So, now in today's class what we do is, suppose go back to the same problem. Suppose I am having a wire, and suppose this is the wire, and which is perpendicular to the plane, and the current is flowing. If the current is flowing, the magnetic field that will produce is surrounded like this. It is surrounded like this, and the current is moving upward. Okay. So, here the current is moving out of the page. And second thing is that magnetic field, the corresponding magnetic field is circulating around. is circulating around. So, the value of the magnetic field we know for this case, because if the wire is infinite. So, I am going to use the result that we got here, the first result. So, this will be the amount of magnetic field. So, if I write it down, so it should be B equal to mu 0 I divided by 2 pi, and if the length is S, then S and phi unit vector. dl, if I calculate the line element here, then it should be ds s plus s d phi phi plus dz z. So, that should be the line element. So, that means if I want to integrate over this line, this circle line, then what is the value? So, that precisely we will do. So, if I want to find out the B dot dl, this quantity, then we can see that the dl, the contribution of the dl should have with this phi, and eventually we have mu 0 I divided by 2 pi s and then s d phi, and phi s will going to cancel out here and here. So, we have something like mu 0 I divided by 2 pi and then d phi. Now, what we do, we will going to integrate over the. So, this is the, let me draw it once again. So, I have the current which is coming out the page, and then I have the magnetic field surrounding this current. So, this is the current that is flowing, and this is the amount of magnetic, this is the magnetic field, this is the way magnetic field is generating. Now, I am going to integrate this closed line. So, if I make a tangential in each point, so that should be the direction of the magnetic field. So, magnetic field is this, every time the tangential line is a momentarily direction of the magnetic field, but it is revolving like that, in this way it is circulating. So, I integrate the closed line integral, if I do, of B dot dl. So, what we get is mu 0 I divided by 2 pi, and then I integrate this quantity 0 to 2 pi, because this is my d phi, and I am integrating over entire circle. So, that quantity is simply 2 pi. So, eventually I have mu 0 I. Now, B dot dl integration, B dot dl integration is, so okay. So, let me first write it. This is a very important expression. So, closed line integration of B dot dl is mu 0 I, but now I write I as I enclose, because the current, the line, whatever the circular line I am drawing here, the current is inside. So, that is why I write this current is enclosed. So, it is indeed a Gaussian kind of law. So, sometimes it is also called, because in electrostatic we had a similar law where we had E dot ds is rho I q enclosed divided by epsilon 0. So, here we are having the similar kind of. So, electrostatic, what we got is this in electrostatics. What we had is this for electric field, E dot ds, that was q enclosed divided by epsilon 0, and that was the Gauss's law in electrostatics. Here we have exactly similar kind of things, but instead of having the surface integral, I have a line integral, closed line integral, and instead of having 1 by epsilon, we have mu 0, and instead of having q, I have I. Q was the static charge there, now here is a steady current. So, for every time when we are dealing with the magnetostatic problem, I need to have a steady current. Last day we mentioned that. So, this is Gauss's law in magnetostatics. Gauss's law in magnetostatic. Now, I enclose, what is I enclose? Let us now look carefully. What is the meaning of this I enclose? That is the current density. If I have some current density J, then that dot ds. Suppose I have a current carrying wire like this. So, this is, suppose this is the wire, I make a cross section of this wire, and this is the axis, any arbitrary shape wire, and I have the axis. And if I now draw a circle around this point, so this is the, like the Gaussian surface, now I have a Gaussian circle like this. Sometimes it is called Amperes loop, we will discuss this later. So, this is, as I mentioned, is called like the Gauss's surface. Here I just draw Amperian loop, and this is the cross section of the wire. And the current that is flowing through is the amount of current that we call the I enclose. So, I should write it here, the I enclose, as this one. So, current is flowing here. So, this amount is I enclose, which is here in this cross section, in this circular inside the Amperian loop, whatever the current is flowing, that is I enclose. Mind it, also some amount of current is flowing, because through the entire wire the current is flowing, but we are only considering the I enclose for this region, only for this region, but other region also having the flow of the current. The current is also flowing outside this region. Here also the current is flowing, these regions the current is flowing, but inside the Amperian loop, whatever the current I am writing is the amount of current that we call the current enclose. Now, J is current density, and obviously if I know the current density, I can write the enclosed current is nothing but the integration of J dot ds over this region, and that is precisely I wrote here, right. Now, let us exploit this expression to find out the another form. The integral form is there, so I am going to exploit this. So, B, we find B dot dl is equal to mu 0 I enclose, and I enclose I can write in terms of the current density J, and if I do, it should be J dot ds. Now, applying the Stokes law, this I can write as integration, surface integration curl of B dot ds, and that amount is that amount here is mu 0 integration of j dot ds. Now, this is true for any kind of surface. So, I can have the expression curl curl of B is simply mu 0 j, which is nothing but the Amperes law. Okay, so far we have, I already wrote that today. So far we have divergence of B is equal to 0, that we proved few class ago, and now today we write curl of B, which is a non-zero quantity, is mu 0 j, that we. Now, let us now look carefully at these two equations, these two very important equation. So, this is always true, grad divergence of B is 0, this is always true, and this is always true, and it reflects the fact that magnetic monopole does not exist. Okay, but is this always true? Curl cross B equal to mu 0 j, this is this always true? The question and the answer I should write here is not always true. This is Amperes law, this is not always true. So, I should write here a note that the Amperes law is only valid for magnetostatic. That means, or that is, the field from the current distribution which is always steady. which is always steady. What is the meaning? That means constant in time. So, the Amperes law is only valid for the magnetostatic, and what is the condition of the magnetostatic in the first class? Exploiting the continuity equation, that was divergence of J is equal to minus of del rho del T, that was the condition. And we mentioned that in magnetostatic we have always a steady current, steady flow of current. So, del rho del T, that condition has to be 0. So, eventually the divergence of J comes out to be 0. The same thing we will going to show here, that but it is not always true. So, curl of B, we say it is mu 0 J, but I am saying that this is not always true, because if I make a divergence both the side, what happened? Let us check. I make a divergence of both the side. So, divergence of curl of something has to be 0. It is identically 0. There is no condition. This is unconditionally 0. What about the right hand side? In the right hand side, I have mu 0 divergence of J. Now, as I mentioned, this quantity is unconditionally 0. That means this quantity has to be 0, always 0. But so that implies, which implies this has to be 0, but this is not always, because we know that from the continuity equation that this is not 0, rather this is minus of del rho del T. So, under which condition this is 0? When del rho del T is 0, that is precisely we are saying. So, this is 0 means that when del rho del T is 0, that is the condition. So, left hand side is always 0, but right hand side is conditionally 0. So, that creates some issue. So, we will going to solve this later on. So, that is the contribution of the Maxwell, and del rho del T equal to 0 is simply the condition for this static case. So, this is the static system. For static system, we have this to be 0. Well, in time dependent system, that means the Amperes law need to be modified. So, in time dependent system, so that means in time dependent system, the Amperes law, which is true only under this condition, need to be modified. Needs to be modified. So, we will see later how we can modify that. Now, let us so these two very important thing now we derive directly from the Bauer-Savart law. So, we already have. So, next thing is the divergence and curl of B. The divergence and curl of B, which we already derive, but here we do it. This is a formal derivation starting from Biot-Savart law. So now the result is already known, that divergence of B we should get 0 and curl of B in magnetostatic it should be mu 0 j. But exploiting the Biot-Savart law, the formal derivation is there. So, we will try to do that here. So, the Biot-Savart law says B at some point r should be mu 0 divided by 4 pi, and then integration of j at r prime cross r minus r prime whole divided by r minus r prime cube dv prime. That is one form of the Biot-Savart law, which includes the current density j. Now we know, so what was r? So let me quickly draw the coordinate systems. So here we have a coordinate system and the wire is something here, and the magnetic field I want to find out here. So this is the point. So this is my r, and the location here from which I calculate the magnetic field is curly r, and from this location to the source point, from the origin to the source point, that is my sorry, not curly, this is r prime. I need to be careful enough in writing the notation. So this is r prime. So these are the three vectors that was involved here. So that means from here I can write this, my r is r minus r prime, that is my r. So let us replace this in the expression of the Biot-Savart law. So the B now as a function of r is mu 0 divided by 4 pi, then integration of j which is at r prime. Now I write small r and this curly r square dv prime. This is my Biot-Savart law. Now I simply try to find out what is the divergence of this quantity where right hand side is there. So if I make a divergence, so I should write this mu 0 divided by 4 pi, and then I put this divergence inside, and divergence of this quantity j r prime r vector divided by r square dv prime. Okay. And sorry, there is, I am missing a cross here. So cross is always there. So this is cross. So so I eventually need to evaluate this quantity. So divergence of j which is a function of r prime, and then cross r divided by r squared. This divergence operator is operating over r. So if I expand this, so this quantity is simply r divided by r square, and then divergence over j which is at r prime, and minus j dot this cross r minus r square. Just exploiting the vector identity, I can get this. Now, okay, so okay, I am making a mistake here. So this is curl, because here we had a curl divergence. So it should be okay, it should be dot of this quantity, okay, and then j dot of that quantity. Yeah, now it is correct. So I mixed the dot here. So curl of j at r prime, this has to be 0, because r is j depends on the prime variable, and this operator is non-prime. So that is, and also the curl of r unit vector divided by r square, it has to be 0. So both the cases it is 0. So that tells us simply from the left hand side and the right hand side, I can write that divergence of B is simply 0, and I calculated that exploiting the Biot-Savart law, the formal calculation. Now the next one, which is important. The next one is how to calculate the curl. So curl of B, which is a function of r, is simply mu 0 divided by 4 pi. B I know, exploiting the Biot-Savart law, I find it. So it is curl over, then we have j cross r square. That should be the form dv prime. Now again I need to use the vector identity, curl of say j, which is a function of r prime, cross r divided by r square. So it is j, and then I have divergence over r divided by r square, and minus j dot this, and that should be operating over r divided by r square. Please note these vector identities. Now the divergence, the derivative. So here all the derivatives. Also we have other few terms. So please note it. The derivative of j term, all the j terms are dropped. As j is a function of prime coordinate. Okay, because j is function of r prime, and whenever this operator is operating over j, it gives rise to 0, that we already got. Now let us remind a very important vector identity that we also proved, that divergence of r divided by r square. We had it here, we had it here, here we are having this. So that thing we know, because we derived it in the initial few classes, that is 4 pi delta cube r. Delta cube stands for the 3-dimensional delta function. So minus of j dot this quantity r unit vector r square, this is also there, is now I can write, because it is operating over r prime, it is operating over r, and inside the r we have prime and non prime both. So, I can make it prime, this operator can make, I can make it prime, and in order to do that, so r vector is r minus r prime. So, whenever I change this operator to prime, this negative sign will going to absorb. So, I should have j dot this prime that is now operating over r square. Okay. Now, the x component, if I calculate only, so I have j dot this operator prime, and the x component of entire stuff is x minus x prime divided by r square. R square is a scalar, and that will going to operate over x. So, what is this quantity? J dot this operator. So, this operator will be simply j x del prime x plus j y del prime, sorry, this operator should be something like this, j y del prime and j z del z prime, or in short notation it is del I prime. This is the operator. This is going to operate over the entire stuff. So, this simply simply gives like this operator is operating over this x minus x prime over r square. I can split this stuff j. So, this operating over that means this minus of plus of these things. So, I can put it here. So, that quantity. So, this operator that is operating over this x component and then over j. So, that thing I can split into two part, this one and this one will appear. So, these things I can write in this way. So, just exploiting the vector identity, and also this operator, how this operator looks, I also write in the left hand side. So, please check it by doing this once. Now, for steady current, we have this equal to 0. So, for steady current, if we have this 0, then eventually we have minus of j prime dot this r over r cube, the x component of that stuff is simply x minus x prime over r cube and j vector. Okay. So, now I am going to use this into the integrate. So, integration, the volume integration of this quantity which is there, which is x minus x prime divided by r cube, and then we have j over dv prime in surface if I now write in terms of surface integral. So, this is simply x minus x prime over r q j dot ds prime, just using the Gauss's law, volume integral to surface integral. So, the closed surface, now this closed surface integral vanishes for a large surface. If I take a sufficiently large surface, then this r should be, this is 1 by r, because the surface here ds will be r square and the dependency is 1 by r. So, these things eventually vanishes. So, if this is not there, then I can have only one term remaining, and hence I can have curl cross B is equal to mu 0 divided by 4 pi, and we have the term that we know, that r prime, and we have 4 pi delta r. So, it is eventually delta cube. So, r I can write at r minus r prime, and that is over the entire volume integral, because rest of the term is 0. So, please check it that I had the curl of both side. So, when I calculate this curl, so this curl is containing two term, one is this one and another is j dot this thing. So, this is my term number 1 and this is my term number 2. So, term number 1 is sustaining because term number 1 is calculating. So, this is my term number 1 here. Whatever the term number 2, this term number is minus of these quantities term number 2. So, I write it term number 2 here. So, this is my term number 2, and this second term is vanishing if I take a very large surface. So, that will not going to contribute here anymore. So, in that case, finally, we have, because this is related to delta function, I simply have now mu 0 j r. So, I find that curl of B is equal to mu 0 j, that I wanted to prove, and I show that exploiting the Biot-Savart law, just the formal derivation starting from the Biot-Savart law, we calculated that. So, with that note, I would like to conclude here. I do not have much time today. So, thank you very much for your attention, and see you in the next class.